Hello everyone, welcome to the 11th lecture of the lecture series on open channel flows. In this lecture we will continue our discussion on gradually varied flows in open channels. Now in the last lecture we introduced the concept of gradually varied flow. We elaborated different aspects of it. We derived a governing differential equation describing the flow, and we started discussing on different classifications of gradually varied flow. We started on the classification of different channels based on their slopes, and we know that the open channels can be broadly classified into 5 groups as per the flow, and those 5 categories are mild slope channels, steep slope channels, horizontal channels, adverse slope channels, and critical slope channels. So now with that concept, let us start discussing on extend the concept of different categories of the flow. So a GVF profile is always either rising or falling, because the name itself is quite evident that the flow depth is gradually varying. So there are two possibilities, of course. Either the flow depth is water profile or water surface is rising or falling. Now as per the mathematical model of the gradually varied flow is concerned, there is it's quite evident that from the mathematical model that the rising or falling trend of the gradually varied flow profile can be shown by the slope of it, the dy dx on the left hand side. The equation of gradually varied flow, what we derived in the last lecture, has been shown in the inset on the right hand top corner, and here we can see that dy dx can be positive or negative depending on the terms on the right hand side. So when the slope or dy dx is positive, then the water surface has a rising trend and the flow depth increases in the direction of the flow, whereas when dy dx is negative, or the slope of the water surface is negative, then the water surface is falling and the flow depth has a decreasing trend in the direction of the flow. There are a couple of schematics of gradually varied flow shown on the slide. On your left hand side, there is this example where the water surface is falling, and so evidently the slope of the water surface dy dx is negative for that case, whereas for the schematic shown on your right hand side, you can see due to a control structure there is a backwater curve has been formed, and in this case the water surface is rising, and evidently the slope of the water surface is positive and the flow depth is increasing in the direction of the flow. Now from the GVF equation, couple of forms of GVF equation has been shown on the slide again in inset on your left hand and right hand sides. So they are the different forms of the same equation. So from that equation we can imply that dy dx, or the slope of the water surface, is positive if the numerator of the equation equation on the right hand side is greater than 0 and the denominator is as well greater than 0, or if the numerator is less than 0 and at the same time the denominator is also less than 0. Uh, so we know from our previous discussions that for the channels of first kind, the conveyance K, which equals to the product of the channel cross section into hydraulic radius r to the power 2/3, so K equals to A r to the power 2/3, is a unique and function and single valued function of the flow depth. Hence, from the couple of conditions shown, discussed above, we can infer that the slope of the water surface dy dx is positive if either y is greater than y naught and y is greater than yc. That means the GVF flow depth is greater than the normal depth and GVF flow depth is greater than the critical depth. This condition has been presented as equation 1 on this slide. Condition number 2 says that, which corresponds to the condition number 2 just shown above, that either y is greater than y naught and y is greater than yc. That means the GVA flow depth has to be less than the normal depth as well as it has to be less than the critical depth. For the first case, of course, given by equation number 1, the flow conditions are subcritical, and for the second case, evidently, when the flow depth is less than the critical depth, the flow conditions are supercritical. Similarly, when dy dx is negative, it's possible for two cases. If yc is greater than y naught, which is given as equation number 3 on this slide. This means that the GVA flow depth lies between the normal depth and the critical depth, and the critical depth is greater than the normal depth. And there is the second case is, again, the GVA flow depth lies between the normal depth and critical depth, but in this case the normal depth is greater than the critical depth. So we have discussed about CDL, or the critical depth line, and NDL, the normal depth line, which are of course two imaginary lines describing the flow. And for the two cases, we can say that when yc is greater than y0, the critical depth line lies above the normal depth line and the flow condition is supercritical, whereas when y naught or is greater than yc, that means the normal depth is greater than critical depth. So then the NDL, or the normal depth line, lies above CDL and the flow conditions are subcritical. So before we talk about different GVF profiles and their behavior, let's talk about the characteristics of a GVF profile at some key points. We have again shown the GVF equation in the inset, and also a diagram on your right has been shows that shows different GVF profiles and some key points, and this equation and the diagram we will refer for our discussion. So key point number 1 is the point when the flow depth approaches the normal depth. So in other words, y tends to y naught. In that case, referring to the equation, we can see that the slope of the GVF profile almost vanishes, or dy dx tends to 0, or we can say that the water surface approaches the normal depth asymptotically. Here the normal depth acts as an asymptote and the water surface approaches the normal depth asymptotically. In the diagram on your right, for the top profile, which has been which is given as M1 in the diagram, we can see that the M1 profile on the left tends to touch the NDL asymptotically. So that's exactly what happens when a gradually varied flow profile tends to approach the normal depth. Key point number 2 is the case when the flow depth tends to approach the critical depth, that is when y tends to yc. So in that case, referring to the equation at the top, we can say that the slope of the GVF profile tends to attain a very large value, or in other words, dy dx tends to 0. Dy dx tends to infinity. So because the numerator on the right hand side of the equation tends to 0. So from the equation also, it's very clear that the water surface meets the critical depth vertically, or it tends to attain a slope which is very large. This is although a very theoretical or mathematical implication from the GVF equation. In reality, what happens is that when the flow depth tends to approach the critical depth, due to the high curvature of the streamlines, as we can see that when the water surface or the slope of the water surface tends to attain a very large value, the streamlines also attains a very large curvature, and in that case, due to the high curvature, the streamlines violate the GVF assumption, or in other words, the GVF flow equation shown on the right hand side is not valid anymore. So this is just a this nature is just thus only a theoretical implication. So in the diagram on your right hand side again, the profile which has been shown given as M2, it tends to approach the critical depth vertically, and since GVF does not really exist when such a high curvature of water surface takes place, the profile has been dotted when it approaches the CDL, or the critical depth line. Thus M2 in the figure, we can see that on the right hand side it approaches the CDL and the profile has been dotted over there. Similar things happen for M3, the profile M3 as well. We'll discuss more about M1, M2, M3 shortly. So key point number 3 is the case when the flow depth attains a very large value. So in that case, when we can say that when the slope of the channel becomes milder and milder, so the flow depth tends to attain a very large value, and in that case the GVF profile approaches the channel GVF profile actually shown by the equation again, it tends to add the slope of the channel, slope of the GVF profile tends to be equal to the channel bottom slope, or S naught. In other words, from the equation we can say that the numerator and the denominator on the right hand side of the equation, they almost become equal for a flow depth which is very large, and in that case the water surface slope becomes almost equal to the channel bottom slope. So keeping in mind all the discussion we had so far, we will now discuss about different types of GVF profiles. So we will classify the GVF profiles based on the channel type. The channel type has already been classified on the basis of the channel slope, and different flow regions 1 to 3. We also have discussed about different flow regions and the flow condition. So by flow condition we mean that the flow depth as compared to the GVF flow depth as compared to the normal and the critical depth applicable for the channel. So the GVF profiles can be classified broadly into 12 types. The types have been enumerated below in the table shown here. So the first column of the table shows the channels of different types with channels of different types with different slopes: mild slope, steep slope, critical slope, horizontal bed channels, and adverse slope channels. Column 2 of the table shows different regions 1, 2, and 3. Column 3 shows the flow conditions, as we have said that the flow condition here means the flow depth as compared to the normal and critical depth. And column number 4 in the table shows the actual classification of the GVF profiles. There are 12 profiles shown here, and we'll start with the mild slope one. So for the mild slope channels for region 1, when the GVF flow depth is greater than the normal flow depth and the critical flow depth, the type is called the flow type is called M1. When the GVF flow depth is greater than the critical flow depth but less than the normal flow depth, the profile is called as M2. And when the GVF flow depth is both less than the normal flow depth and the critical flow depth, the GVF profile type is called M3. Now keep in mind that these are mild slope channels. So for mild slope channels, the normal depth will always be greater than the critical depth. That means NDL will always lie above CDL, and the flow conditions will thus always be subcritical. So for steep slope channels, also there are 3 types of GVF profiles for 3 regions 1, 2, and 3. Again, for steep slope channels, referring to our discussion earlier, YC will always be greater than Y naught here. All the critical flow depth will always be greater than the normal flow depth, or in other words, the CDL will always lie above NDL for this type of channel. So here when the gradually varied flow depth Y is greater than YC is greater than, and which is greater than Y naught, the GVF flow type is called S1. When the GVF flow depth lies between YC and Y0. In region 2, the type is called S2, and for region 3, that's the bottommost region, when YC is greater than Y0 is greater than Y, the GVF flow type is called S3. Extending the same concept for critical slope, there are two regions possible only. We know that for critical slopes, CDL and NDL, they coincide, because the critical flow depth is the normal flow depth. And so here there are two cases possible. One is that the gradually varied flow depth will be greater than the critical flow depth or the normal flow depth, and in that case the GVF flow type profile type is known as C1. And for region 3, when gradually varied flow depth is less than the critical flow depth or the normal flow depth, the profile type is known as C3. For horizontal bed channels, when the channel bottom slope is 0, we know there are two regions possible. We also have discussed that for horizontal bed channels and adverse slope channels, uniform flow is not possible. So the NDL, the normal depth line, will be is non-existent for these type of channels, and for both horizontal bed and adverse slope channels, the flow region 1 is thus absent. So for coming back to horizontal bed channels, there are two cases possible, that's why. And for region 2, when gradually varied flow depth Y is greater than the critical depth YC, the GVF flow type is known as H2. And for region 3, when gradually varied flow depth is less than the critical flow depth, when the flow is supercritical, the GVF flow type is called H3. For adverse slope channels also, there are two regions and two cases possible. When for region 2, when Y is greater than YC, the flow profile type is called A2. And for region 3, when Y is less than YC, that means the flow is supercritical, the channel the flow type is known as A3. So whatever we have discussed in the last slide, we'll now present that diagrammatically, and we will show all the profiles by schematics here. For example, there are in the diagram on your left hand side, we can see three mild slope profiles, M1, M2 and M3. This shows how the profiles look like in real life. And these are of course mild slope channels, so NDL is above CDL again. And note that here all the curves in region 1 for any slope, for channels of any slope, the curves which are in region 1, they have positive slopes, and these curves are called backwater curves. The curves, whereas the curves in region 2, they will always have negative slopes, and they are known as drawdown curves. So note also one feature, that in these diagrams the vertical scale has been exaggerated. That means that the horizontal extent of the curves is really big, whereas the vertical slopes and the vertical features are small. But to show that in the diagram, the vertical scale has been exaggerated, which is not to be mistaken in real life. So here on the left hand side again, we can see three curves for mild slopes, M1, M2 and M3. We have already discussed the features of those curves in the last slide. In the diagram on the right hand side, we can see three curves for the steep slope channels, S1, S2 and S3. In this slide, we can see the diagrammatic representation of the GVF profiles for critical slope channels, horizontal bed channels and adverse slope channels. So as discussed before, critical slope channels have two GVF profiles possible, C1 and C3, one above NDL or CDL and one below that. For horizontal bed channels, also there are two cases possible, H2 and H3. So here region 1 is absent. So H2 is the profile above CDL and H3 is the profile below CDL. For adverse slope channels, in the last figure on this slide, also there are two cases possible, A2 and A3. Again, region 1 is absent here. So A2 is the profile which is above CDL and A3 is the GVF profile below CDL. So having discussed and explained about different types of gradually varied flow profiles and different features of them, let's now discuss on some instances or practical instances where this different types of GVF profiles occur. For example, we take the M profiles or for the mild slope channels. The M1 profiles, for example, which represents the subcritical flow conditions, they occur when there is an obstruction to an open channel flow by dams, weirs, barrages or other control structures. Also when there are natural features such as bains. So for those cases, behind those control structures or hydraulic structures, M1 profiles occur. We can see the example, the pictorial representation of M1 profiles on your right hand side. So the profiles start from behind the obstruction, let's say behind the dam or the weir or the barrage, and they continue behind the hydraulic structures for several kilometers, and they tend to approach the normal depth line asymptotically. M2 profiles, which is the mild slope profile for mild slope channels, but for region 2, this profiles occur when the flow encounters a sudden drop in the channel beds or at channel transitions of constrictions and at the canal outlet into reservoirs like pools. So a pictorial representation of M2 profile has been shown on your right, which shows that a uniform flow, when it encounters a pool or a sudden drop on the right hand side, it approaches the pool or the drop by the M2 profile. M3 profiles are the GVA profiles for mild slope channels and for region 3, and this M3 profile occur when a supercritical flow stream enters a mild slope channel. The flow downstream of a sluice gate or a spillway of a dam are example. For example, we can in the diagram on your right hand side we can see a sluice gate, which behind the gate there it holds the reservoir water, and when the gate the water is released, it first attains a rapidly varied flow profile, and after that it approaches a hydraulic jump. We will discuss about hydraulic jump later when we discuss about rapidly varied flow in our course, but for the time being, let's take it for granted that there is a hydraulic jump which takes place downstream of a sluice gate. So when the flow is released from the sluice gate, it first attains a RVF profile, which has been shown in the diagram, till the vena contracta, and then it approaches the hydraulic jump in the downstream by a gradually varied flow profile, which is the M3 profile. M3 profiles, unlike M1 or M2 profiles, they are rather short length ones. This is a characteristic of the M3 profiles. M3 profiles start here as shown by in the diagram. It starts at the vena contracta on the left hand side and ends in the downstream with a hydraulic jump. So having discussed about M profiles, let's now focus on S profiles, or the profiles which occur in steep slope channels. So there are three profiles possible: S1, S2 and S3. S1 profile occurs when a supercritical flow in a steep channel encounters a deep pool which is created by an obstruction in the flow path. We have discussed that the obstruction to a channel exists when there is a dam, a barrage or a weir, or any other hydraulic control structures. So when there is a steep slope channel and it encounters an obstruction created by that dam or barrage or weir, an S1 profile is produced. The S1 profile has been shown on your right in the diagram, and S1's curve starts subsequent to a hydraulic jump. So when there is a reservoir, a huge reservoir created due to the existence of the dam or weir, and there was let's say a uniform flow was taking place in a steep slope in supercritical conditions. So it tends to attain the height of the reservoir by a hydraulic jump, and then subsequent to it by a gradually varied flow, which is given by S1 profile. The S1 profile is also a very large length profile, which starts again from the hydraulic jump on the left hand side and trying to meet the pool level asymptotically on the right hand in the diagram. S2 profiles are produced when the flow from a reservoir encounters a steep channel downstream of the flow, or when a flow in a mild slope channel encounters a steep channel in the course of the flow. When a mild slope channel encounters a steep slope channel, that is called a breakout grade, or even for the cases which other way around. So when there is a break of grade, this S2 profiles occur. We can see the pictorial representation of the S2 profile on your right hand side, which starts from the pool level of the reservoir on the left hand and approaching the normal depth line NDL asymptotically again on the right hand side. S2 profiles are rather short length profiles, unlike S1. S3 profiles, which is the gradually varied flow profile on the steep slope channels in the region 3, they occur when a supercritical flow stream enters a steep slope channel. We can see that on the in the first diagram on the right hand side that the flow downstream of a sluice gate, when it encounters sluice gate or a spillway, encounters a steep channel, so an S3 profile is produced, and S3 profile starts downstream of the sluice gate and tries to attain the normal flow depth on the right hand side again asymptotically. S3 profiles can also occur when a flow in a steeper channel encounters a less steep channel. So in that case as well, which is shown by the second diagram at the bottom, that when uniform flow in a steep channel suddenly encounters a channel of less steepness, then it approaches another normal depth asymptotically by S3 profiles. So for critical slope profiles or C profiles, there are two cases possible, C1 and C3. So for critical slope channels, the NDL and CDL, of course, they coincide, and there is no region 2. Thus there are only two curves possible, C1 and C3. Instances of C1 and C3 profiles are rather very rare in nature, and those are very unstable. Since the slope is critical, this makes the flow really unstable, and so when the critical flow depth, when the gradually varied flow depth is greater than the critical depth, the flow profile is called C1, and when the gradually varied flow depth is less than the critical depth, or the flow is supercritical, then the gradually varied flow depth is known as C3. For horizontal bed channels, of course, the uniform flow is not possible, so there is no NDL here, and there are two, the region 1 is thus absent here, and there are two profiles possible, H2 and H3. H2 and H3 profiles are similar to M2 and N3 profiles, as horizontal bed bed channels are the special case when the mild slope channels, the slope of the mild slope channels tends to 0. So we can see an example of an H2 and H3 profile in the diagram at the bottom. So H3 profiles here occurs downstream of a sluice gate in a dam or a weir, and it starts from the downstream of a sluice gate and ends downstream at the start of a hydraulic jump. H2 profiles whereas can occur downstream of a hydraulic jump, and however H2 has a horizontal asymptote here. For adverse slope channels, we know that the uniform flow is not possible as well. So adverse slope curves are also very rare, and they are similar to H2 and H3 curves. These profiles are very short-linked ones. So an example pictorial representation of an A2 profile has been shown in the diagram below, where when an adverse slope channel uh, ends in a pool or a reservoir, so an A2 profile occur, and for the A2 profile, which is the gradually varied flow profile in the region 2 for adverse slope channels. It starts from a uniform flow depth on the left hand side and ends in the pool or the reservoir on the right hand side. So that will be all for this lecture. We'll see you in the next lecture. Thank you very much.